Okay, well, it's a really great pleasure to welcome Sarah Russell to give this Ed Scott talk. I'm going to just very briefly say a couple of things about Sarah. Sara, she did her undergraduate at Cambridge, her PhD at the Open University. She then went and did postdocs at Caltech and the Smithsonian, returned to the UK to work at the Natural History Museum, where she's a professor of planetary sciences and leader of the planetary materials group. She's a fellow of the Meteoritical Society and of the Royal Astronomical Society, but most importantly of all, she's got an asteroid named after her, which is always great. So without further ado, I'll ask Sara to give us this Ed Scott lecture. Thank you.
Brilliant. Thank you. Thank you so much for that introduction, Richard. And thank you, Ian and Richard, for inviting me to give this talk. So it's a real honor to give an Ed Scott lecture. Of course, Ed was a real giant in our field. Hang on, I'm just going to hide my face so I can see my screen. So today I'm going to be talking about the nature and distribution of type 1 chondritic material, and it's based on a paper in MAPS that I wrote with Martin Suttle and Ashley King. It was kind of like a lockdown project for us that we went through a lot of the literature about type 1 material, and so I'm going to go through that today. So first of all, we're going to start with, if I can go forward. There we go. Tiny bit of history. So actually, the nomenclature of type 1, 2, and 3 for carbonaceous chondrites is the oldest way in which carbonaceous chondrites were classified. So this nomenclature was coined by Wick in 1956, based on his chemical analysis. So he was actually looking at 3 different chemical groups, but he interpreted, well, but he gave them the names of 1, 2, and 3. And then later on, Brian Mason suggested that it's the abundance of water that is the real kind of defining feature of these 3 groups. And so that's how petrologic types for carbonaceous chondrites began. I want to start off as well with the definition. So when I put in what is type 1 into Google, it said it's a type of diabetes, which is not what this talk is about. And if you think it is, then I'm afraid it's going to be a bit of a disappointing hour for you. So I'm going to use type 1 as a description of chondrites, which I use to include material returned from space missions as well. And they are chondrites that are completely affected by the action of water, so that anhydrous silicates are rare or even completely absent. So we'll go into exactly how we get the definition when we talk about the CM meteorites, but the abundance of anhydrous silicates is typically less than 10% and often a lot less than 10%. So type 1 chondrites are always carbonaceous. And the aqueous alteration reactions predominantly occurred on the parent body. So there's a huge amount of petrologic evidence to support this, which is summarized in Adrian Brearley's paper in 2006 in Meteorites and the Meteorites in the Early Solar System too. And just a note as well, so this talk is summarizing a lot of literature, and I'm going to put some of the key papers at the bottom, and I've written out the names of the papers to make it easier to Google them if you want to delve into any of these things a bit more closely. So they became aqueously altered because they accreted with water ice and possibly and or hydrated silicates as well, which is the source of the water. And as well as water ice, they could also have contained other ices such as carbon dioxide, which precipitates as carbonate, and ammonia, which changes the fluid composition to more alkaline values. Okay. We can analyze type 1 material in the form of several samples. So the sort of typical thing people think about when they think about type 1 material is meteorites. And of course, we will discuss those. But also type 1 material is found very abundantly as xenolithic class in other meteorites. So not the whole meteorite themselves, but just a little piece of the meteorite. Also, micrometeorites and IDPs often have type 1 material. And we also now have type 1 material in the form of sample return material that's from asteroids Bennu and Ryugu. So we're going to discuss all of these in turn. And then we will, well, then I'll try to summarize and come up with some interpretation of it all, hopefully. Okay, so starting off talking about meteorites. And so first of all, I wanted to talk about generally the abundances of carbonaceous chondrites. So carbonaceous chondrites are classified according to their petrologic types from type 1 to type 7, where type 1 has been completely altered by water, as we've discussed. Type 3s have experienced little alteration, so they are best at preserving their nebular abundances. And then 4 to 7 have been progressively heated to higher and higher temperatures. So for the carbonaceous chondrites, the most abundant types, the CM2s, the CO3s, and the CV3s. But you'll see that many of the chemical groups also have type 1 examples. But overall, this is a very rare type of meteorite. So there are only 45 type 1 meteorites listed in the Meteoritical Bulletin, out of a total, which I checked yesterday, of nearly 86,000. So that works out about 0.05% of all meteorites are type 1. So they're incredibly rare in our meteorite collection. But as we'll discuss as we go through the talk, they are actually much more abundant in space, and it shows how biased our meteorite collection is. So we will go through all of these chemical groups in turn, starting off with the CI chondrites. So the CI chondrites are, of course, what my kids would call the OG of type 1 chondrites. So they're often, the term CI is used synonymously with type 1, of course, wrongly. But these were the first recognized type 1 meteorites. On the left there is an example. So this is the Avuna meteorite from our collection at the Natural History Museum. You can see this beautiful fusion crust facing the camera. And then you can see the rock is made of a fine-grained black material with some white effervescence on the surface. So there are only 5 meteorite falls that are true CIs plus 1 recent find, and this map shows where they landed. And they span, although there are a very, very small number of meteorites, they really, they span, as you can see, the globe with 4 continents having a CI fall on them. And they also span time from LA, which fell in 1806, at a time when we were just discovering that rocks could fall from space and become meteorites, all the way to Ujbeka 002, which was just found last year. So although it's a find, it's an incredibly fresh CI chondrite. They also range massively in size. So you can see here Revelstoke and Tonk are both very tiny. At the time, Revelstoke, when it landed in 1965, was the smallest meteorite ever recovered. And that goes all the way up to Orgueil, which has a massive 12 kilograms fell in France in 1864. And this fell as a shower of stones. And one of the stones was supposed to be so big, it was as big as a human head. So sadly, that stone no longer exists. And then, of course, there's Avuna, the type specimen for this meteorite group, which fell in Tanzania in 1938. And fun fact about Avuna is that it was retrieved from the branches of a tree that it fell into. Okay, so what do we need to know about CI chondrites? So although they're very fine-grained, we can investigate the mineralogy of CI chondrites using X-ray diffraction. And this is work that was led by Ashley King and published in 2015. And this shows that the modal mineralogy, that is the average mineralogy of CI chondrites, it's actually incredibly consistent. So the CIs, compared to many other meteorite groups, are all very, very similar to each other. They all have between 80 and 85% phyllosilicates. They have abundant magnetite, usually around 8% magnetite. And they also always contain sulfides. Then they often contain carbonates at abundances that can be picked up by the XRD, which means abundances over a percent or so. And sometimes they contain ferrihydrite and gypsum, which are terrestrial contaminants. And you can see as well, looking at the replicate analyses, that they're often different replicates of the same meteorite can be different to each other. So, for example, Aug-2 contains olivine, which we don't see in the other samples of Aug-A. And that's because of the brecciated nature of CIs, that they often have local heterogeneities of a scale of millimeters or so. Okay. And CIs, of course, famously have a composition that is similar to the sun. So if we look at the abundances of the major elements in the as measured using spectral techniques in the sun and compare it to the abundances in CIs, they look incredibly similar. They have a 1-to-1 ratio, and that tells us that the CIs are solar in composition, that they're chemically incredibly primitive. They are just samples of the protoplanetary disk that has accreted without very much chemical fractionation, unlike many other meteorite groups which have lost the volatile components. Okay, CIs, although they are kind of chemically very primitive, they are incredibly susceptible to terrestrial processing. So the white deposits that you can see on the top of the meteorites are all terrestrial sulfates, and Gunnell and Zelensky demonstrated this was true in 2010. So for a long time, these deposits were thought to be asteroidal. They were thought to be due to late-stage oxidizing alteration. But if you look back at the early records of CI falls, the first people to look at the CIs report that they're just black as coal. So they obviously form over timescales of months and years on the Earth's surface. Okay, the other fact, I mentioned this before, but CIs are invariably brecciated. So this is a sample of Aug-A. It's about 5 millimeters across. It's a backscattered electron image, and you can see various clasts in there. So, for example, I don't know if you can see my cursor, but there's a lighter fragment in the bottom left. And then you can see areas that are rich in bright sparkles, which are the sulfides, areas which are sulfide poor, which don't have these bright areas as well. So you can see how clearly brecciated they are. And this is because they tend to be regolith breccias. So they formed on the surface of an asteroid where they were very susceptible to being gardened. Okay, so looking in a bit more detail at the composition, this is an element map which was made by our student Pippa Lewis of the new CI meteorite find, Hayabusa2, which was kindly loaned to us by Jerome Gatacheka. So in this element map, iron is green, and that means that all the sulfides and magnetite show up as bright green particles. Magnesium is red. So you can see that the phyllosilicate matrix, which makes up most of the rock, is very rich in magnesium, and calcium is blue, and this shows up the carbonates. But overall, we can't see any long-range structure in the CIs. We can't see any evidence that it has chondrules or that it ever used to have chondrules. We can't see any rounded features whatsoever. And I will do is zoom in just so that you can see this in a little bit more detail. Again, as you zoom in, you can see green lath-like crystals, which are the sulfides. You can see many, many tiny little green speckles, so that's the magnetite. And you can see carbonates in here as well. And you may be able to see that some of the carbonates are purple in color, so these are dolomite, and some look more bright blue. These are calcium carbonates. But again, as we look in closely, we can't see any structure in it at all, such as chondrule-like features. Okay, so that was a quick introduction to CI chondrites. I'm going to move on to CMs even faster. So, as I mentioned, CMs are one of the most abundant carbonaceous types of carbonaceous chondrite. In fact, there are 774 CM chondrites known, and of those, around 5% are classified as CM1 chondrites. In this talk, I'm not going to talk about types 1 stroke 2 chondrites, which are about the same number as the pure type 1 chondrites. So most of the CM1 chondrites are actually really, really small. The biggest one is Mwapa Valley from Nevada, which is shown there in the picture. But there are only 3 that are actually bigger than 20 grams. So they're very similar in chemistry to CM2 chondrites, but their mineralogy is being completely affected by aqueous alteration. You can still see the chondral shapes that are found in CM2s. And on the picture on the right from Martin Suttle's paper, you can see these rounded features. So it has a lot more kind of structure and things you can see in it than the CIs have. But all of these rounded structures are actually made of phyllosilicates. They're not made of anhydrosilicates. And this is also from Martin Suttle's paper to talk about what happens as you alter a CM from a theoretical CM3, which has not been aqueously altered at all. And we think this is probably made up of anhydrosilicates and metal, as well as sulfides and carbon-bearing ices. And then as the aqueous alteration progressed, the anhydrosilicates broke down and started to form first an iron-rich and then a more magnesium-rich phyllosilicate mass. The iron-nickel-metal formed magnetite, and the sulfides started to form as well. So just focusing in on the CM1s, you see there's this mineral called toshilanite, which is a hydrated iron sulfide, which is really seen in many CM2 chondrites and really only in CM2 chondrites. But it's absent in CM1s, and this is likely because it is destroyed by heating. So it breaks down at about 150 degrees centigrade. And so the fact that it's not seen in CM1s suggests perhaps that why a rock becomes a CM1 rather than a CM2 might be because it was heated to higher temperatures, which enabled these alteration reactions to progress even further than they do in the CM2. Okay. And going to modal mineralogy work. So this is a plot of our X-ray diffraction data for CM meteorites. On the vertical axis is the total anhydrosilicates, which means olivine plus pyroxene. And on the x-axis is the total phyllosilicates. So you can see there's a very clear anti-correlation, as you would expect. So as aqueous alteration progresses, the anhydrosilicates get broken down and form into phyllosilicates. And it's from this diagram that we came up with the definition of type 1 material. And you can see that it's around under 10% anhydrosilicates. That's where you're getting the CM1. So these classifications were all done by eye subjectively, but they tend to have anhydrosilicates less than about 10%, and usually a lot less than that. Okay. Right, rattling on even faster to the CR1. So this is easy to do because there's only one example of CR1, and that's Grosvenor Mountains 95577. So this is a beautiful meteorite, and you can see in the figure on the left that it clearly has chondral-like shapes in it. But then if you delve into these chondral-like shapes in detail, you see that they're actually composed of phyllosilicates, and therefore it's a type 1 meteorite. Yeah, that's all I really need to say about that right now. And next, I have to rattle through this because I have quite a lot of stuff to show you during this talk. But next, we're going to talk about the CYs. So the CYs, you might be wondering why I didn't talk about these when I mentioned CI chondrites, because in the meteoritical bulletin, there are 4 additional CI1 classified meteorites, of which Y980001 is the biggest one. Okay, but there is some controversy about this, and this is because these meteorites have all been heated up, and I will show you an example here. So this is thermogravitational analyses, which shows how much water, basically you heat up a small sample and you measure how much water is derived from it at each temperature. So here, if you look at Orgay and Ivuna in blue, you can see that at low temperatures, lots of water comes off. That's all terrestrial, but also lots of water comes off between about 400 degrees and 800 degrees. And that is because there's water trapped in the phyllosilicate structure. But the Y chondrites, the Yamamoto type chondrites, they do not have water coming off in this temperature range. That's because they've been heated up to over 600 degrees centigrade. And what that's done, it has dehydrated their phyllosilicates. And this really complicates our interpretation of them because it's very hard to disentangle what features in there are due to heating and what were potentially original differences or similarities between them and CI chondrites. So their chemistry is broadly similar to CI chondrites, but their mineralogy is very different. So again, this is X-ray diffraction work showing modal mineralogy of two CY meteorites at the top compared to the CI meteorites that we've already seen. So you can see it has a lot less phyllosilicates, and that's partly because the phyllosilicates have been converted to anhydrosilicates to olivine by this heating process. But also it contains a load more sulfides. And again, this may be due to the heating that they've experienced. But there are other things as well. For example, they have significantly less magnetite than the CIs, and that may be an original feature. Looking at the texture of the two meteorites side by side, you can see how much of a difference it makes that the CYs have this huge amount of sulfide. It really kind of changes the way they look. But again, they tend not to have structure the same way the CIs, but not always. So let me show you some examples. So these are examples both from Y86162, which admittedly is sort of marginal because it's has some features that are slightly type 2-like, but you can see it has large features in here, like there's this big class that's now phyllosilicate, but was clearly once a lithic class. We don't see anything like that in the CIs. And on the right is a vestige of an old CAI, also in Y82162. So these are described in Suttle's paper of 2023. And so these seem to be perhaps evidence that they accreted different material in them than the CIs. It might be something a bit different. However, there's another side to the story. So this is an isotope plot of iron isotope composition as a function of titanium isotope composition, showing nucleosynthetic isotope ratios of various carbonaceous chondrites as well as the CY chondrites. There was a fantastic, actually, review of nucleosynthetic isotopes by Christoph Burkhardt a while ago that gave a great Ed Scott lecture. So I'm not going to go into that now. All you need to know is if it plots in a different part of this diagram, then it may be from a different parent body. And similarly, if it plots in the same part, it may be from the same parent body. And so Zhu et al. Showed that CY1 meteorites tend to plot in the same field as CIs, which may mean that they come from the same parent body. The CY2s are a different story, which I'm not going to go into because this talk is not about type 2 meteorites. Okay, so the Zhu et al. Model suggests that there was an impact on the CI chondrite parent body, and this produced both the heated and the unheated fragments, which ultimately became the CI and the CY meteorites. And therefore, if they're from the same parent body, then perhaps we should consider them the same meteorite group. However, I prefer a model more like this, and we'll go into the number of parent bodies a bit later on in the talk, at the end of the talk specifically. But I think it makes more sense to think about multiple small parent bodies, partly because the accretionary array of CYs and CIs may be slightly different, but also because we don't see any transitional objects. So there's no meteorites that are midway between a CY and a CI, which you might expect if there was an impact onto one body. And secondly, CIs and most CIs and some CYs are breccias, but we don't see lithologies of CYs within CIs and vice versa, which suggests there's not that much mixing between the groups. However, of course, we're talking about a very small number of meteorites, so it could just be that we haven't found the right sample yet. Okay, I need to start going a bit faster. Okay, here's a summing up of the mineralogy of these four groups that contain type 1 examples. So you'll see that in some ways, mineralogically, this is pretty simple. The type 1 mineralogy is dominated by phyllosilicates, carbonates, magnetite, and sulfides in varying proportions. So there's more magnetites in the CIs, for example. There's more sulfides in the CYs. That may all be due to the heating, though. The CRs have got a bit of everything. So I think that these kind of basic four minerals are the inevitable result of the interaction of water and silicate and metal. And there are some examples of the equations that would have taken place shown on the right here. These could have happened under a variety of different temperatures and conditions, but we'll talk a bit more about that later. I want to crack on a little bit. I haven't yet talked about the composition of the phyllosilicate that we've been talking about. So this is a plot of iron, silicon, aluminium, magnesium to show the composition of the phyllosilicates. And marked here also are the lines for smectite and serpentine, two of the main phyllosilicates that we observe in these chondrites. So here the CMs and the CRs, there's the area in which the whole group plots is shown as a kind of ghost, with the area of the type 1 material as a solid circle or blob. The CIs have a composition that's magnesium rich, and it plots between smectite and serpentine. That's because it contains layers of these two kinds of phyllosilicates, serpentine and saponite, which is the CYs have got a similar range of phyllosilicate compositions. I've got a slightly wider range with slightly more iron-rich values. The CMs and the CRs are more serpentine-like in composition, and the type 1s plot at more magnesium-rich regions. And that's because as aqueous alteration progresses, the last thing to alter are the magnesium-rich anhydrosilicates, forsterite and enstatite. Once those get altered and reprecipitate as phyllosilicates, that produces a phyllosilicate that is richer in magnesium. Okay, but there are also a few anomalous meteorites that are type 1. This is a really cool one. This is Flensburg that fell fairly recently in 2019. It is a type 1. It has chondrules in it that again are altered to phyllosilicates, but it doesn't look like a CM1 or a CR1. It has these very interesting acicular sulfides that tend to surround the chondrules. Miller range 090292. So this was first classified as CR1. It's only tiny, so I couldn't find any good pictures of it. But in some ways, it's a bit different to CRs. It has a slightly different mineralogy, has some nickel-rich metal in it, and doesn't have any carbonate in it. It also contains amphibole, which suggests that it may have come from a larger body, which we'll get into. And finally, Bench Crater. This is quite a cool one because although it is recorded as a meteorite in the Meteoritical Bulletin, it didn't actually land on Earth as a natural object. It landed on the moon, and it was brought back by Apollo 12 astronauts. So they retrieved it from a place called Bench Crater. It's fairly small. It's a couple of millimeters across. And again, it doesn't quite fit into any of the classifications that we know. So it has chondrule-like features, which you can see as the lighter areas in the optical image. And you can see in the bottom right image, false color element map, that it contains acicular sulfides surrounding the chondrule-like features, similar to Flensburg, actually. But its oxygen isotope composition is different. Okay, oh yeah, we're going straight into the oxygen isotopes now. So another way to classify meteorites is using oxygen isotopes, and we can use three isotopes of oxygen, 17, 18, and 16. On the Earth, everything falls along the line here, marked TF for terrestrial fractionation, which is a line of approximately slope a half. Whereas many for the CCAM line is the carbonaceous chondrite anhydrous minerals line, along which most carbonaceous chondrite, well, anhydrous minerals fall. And you can see the bulk compositions here of the meteorites. They span a range. And you may think that the more aqueously altered ones tend to be more O16 poor. So we think that this mixing is largely due to a O16 rich poor water and O16 rich solid materials. So you would expect in the CMs, for example, we do see as CMs get more aqueously altered, they tend to get lighter in composition. But if we look at the CM1s and where they plot, they actually don't follow this trend at all. You would expect the CM1s to plot at the top of the CM field, the O16 poor, but they don't. They plot all over the field, which may be partly due to terrestrial alteration, because most of these samples are Antarctic finds, and so their oxygen isotopes may be compromised for that reason. Okay, we're going to crack on now to talk about xenoliths in meteorites. So xenoliths are great because they may be telling us about what was floating around the solar system in the earliest times rather than modern day times. Their abundance is incredibly variable among meteorite types, so they're often abundant. So xenoliths in general, and particularly type 1, are abundant in many carbonaceous chondrites, but rare in ordinary chondrites, and abundant in uralites and howadites. Serena Goodrich and colleagues wrote this great paper about the different abundances in ordinary chondrites and uralites. And the implications for the early solar system, basically suggesting that the uralites have got so many xenoliths because it was actually got disrupted in its early history and became a kind of a rubble pile that was able to then receive xenoliths, carbonaceous xenoliths that were brought into the inner solar system during the giant planet migrations, whereas the most ordinary chondrites hadn't reached that stage at that point, and so didn't get to receive this flux of material at that specific time. Okay, I'll just show you some examples. Here are some examples in carbonaceous chondrites. On the left is a unique cluster in Ishevo. When you read through the literature of this, you read often the phrase "not seen in any meteorite" or "has no equivalent in our meteorite collections." So these xenoliths often have similarities to things that we see in meteorites, but are not quite the same. So this cluster on the left, cluster on the left there, let's go back, is actually has a very CI-like mineralogy, but it has these large rounded carbonates, which we don't see in CIs. On the right is a class in CM2 meteorites. So in CM2 meteorites, the type 1 class are usually CM1-like. And then special shout out to Kai Dun. So Kai Dun is a kind of a trash can of a meteorite. So it is a mixture of carbonaceous and enstatite-like material. But it has all sorts of class in there, including several type 1 class. It has CI-like material, it has CR1-like material, also CM1-like material, all mixed together. Okay. HED meteorites. So actually most xenolite, although howardite meteorites, which are a type of bestoid meteorite, have abundant xenoliths, but they're usually type 2 material. They can be CM2 or CR2. But they also does contain type 1 material, which might be more abundant as smaller class that maybe don't get described so often. And here's a rather a larger example. This is a class from the Bolgati howardite, which is Ci-like. Ordinary and Rumaruti chondrites. So on the left here is a class, looks to me a little bit like a Cy actually, with the abundance of sulfide in there. It also contains abundant magnetite. On the right is again a unique class which has a Ci-like mineralogy, but its phyllosilicate composition is more iron-rich than Ci's, and it also has these veins running through it, which is not seen in Ci's. And xenoliths and polymeteorites, there are loads of these. So these were summarized by a talk that Serena Goodrich gave at the workshop on Bennu and Ryugu recently, and she was kind enough to share her talk with me. So she showed that there are Ci-like chondrites, Ci-like xenoliths in these urolites. There are also Ci2-like materials. So this are things that have a composition rather like Ci's, but also have abundant enstatite and olivine in them. And they also have Ci-like heated xenoliths. So this one, it doesn't look like a Cy to me. It has a lot of magnetite in it rather than sulfide. So it looks like a unique kind of class to me. Okay, micrometeorites. So unmelted micrometeorites are dominated by carbonaceous material, and they rarely contain anhydrous silicates. So that suggests they might be type 1, although they're often very, very small. And again, many of these don't have equivalents in our meteorite collections. So an example is the saponite-rich micrometeorites reported by Sakamoto. And then this lovely picture of a magnetite-rich micrometeorite that Cécile Engron sent me. The Paris group, Béjac et al., estimated that around 5% of Antarctic micrometeorites are Ci-like. So that's a load more than we see in our meteorite collections as a proportion. And looking at the oxygen isotopes of all of these xenoliths and micrometeorites, you can see there's this massive range across the meteorite values that of known meteorites, but also it extends the range up to more O16 pore values. But broadly, I would suggest that there are two kind of camps or families. There's the CM-like ones, which are plot below the terrestrial fractionation line on or around the CM field. And then there's the Ci-like, which plot above the terrestrial fractionation line and have a massive range in delta 18O. Okay, so next I'm going to talk about sample return missions. So this is how meteoricists feel about sample return missions. Very, very excited because these are an opportunity to obtain material where we know where it's come from. That means that we can get both the astronomical context of knowing what kind of asteroid it is and where it came from, and also the geological context of knowing what the specific asteroid's geology was like. We can get uncontaminated samples, and also we can pick them so they'll be less biased by survivability to Earth, so we won't only get the ones that are strong enough to survive coming through the Earth's atmosphere. So there have been 3 asteroid sample return missions so far. The first one, Hayabusa, visited asteroid Itokawa, an S-type asteroid, and showed that it was ordinary chondrite materials. I won't be discussing that further. But the 2 other asteroid sample return missions both brought back type 1 material. So let's look at that. So when Ryugu came back, it actually looked remarkably like a Ci chondrite. And this is a game that Ashley King invented called Ryugu or Ivuna. And you in the audience have to guess which piece you think is Ryugu and which piece you think is Ivuna. They both look so similar. They have this kind of cracked features on them. And so they're very difficult to tell apart. You can see bright patches that are probably sulfides in both. But the one on the left is Ivuna. The one on the right is Ryugu. So I know that because our piece of Ryugu is smaller. But you can see the similarity, and that similarity extends when we look at it more closely as well. So on the left here is a figure from Yokoyama et al., which shows the iron, sulfur, and calcium abundances of these of the return sample. On the right, I've redrafted our OC002 Uchibika 002 element map to have the same color scheme. So it also has red is iron, green is sulfur, blue is calcium. So I haven't got the color balance exactly the same, but you can see the remarkable similarity in texture. They both have these lath-like greeny yellow things, which are the sulfides. They both have the bright yellow sparkles, which are the must be magnetite, and they both have the blue carbonate. So they're really incredibly similar. But I'm going to talk mostly about Bennu, because that's what I've been studying the most. And I don't know if I can't see myself on the screen, but I am wearing my OSIRIS-REx t-shirt for the day. So Bennu is composed mostly of phyllosilicates, also with carbonate, magnetite and sulfide, and olivine. So its texture looks remarkably CI-like in that it doesn't have any features in terms of like no pseudo-chondrule-like features. It's maybe different to CIs and Ryugu in having a greater abundance of olivine, which you can see here as the bright red patches. So it has a fairly significant amount of olivine, which we don't normally see in CIs. Okay, it's extremely brecciated, like CIs are. And here is a section of OREX 80088, which is a stone of interest that the sample analysis team picked to work on because it's what we call a hummocky sample. And these turn out to be extremely brecciated. So you can see from the element map that there are some areas which are more greenish in color. So these have a more iron-rich phyllosilicate matrix, and some have a more reddish color, and these are more magnesium-rich. Next, I'm going to look in more detail at this little area that is highlighted by the white rectangle. So looking at that close up, using the same color scheme, you can see this is the division between two very different clasts. On the right, there's this iron-rich phyllosilicate material, which is almost like a type 2 texture. It's got loads of enstatite and olivine in it. And it looks to me like a little bit like the xenolithic class in urolites that Sarina Goodrich highlighted in her work. And then on the other side of this boundary is the type 1 material. And you can sort of see intuitively, I think, that if the type 2 material became more aqueously altered so that all of these red things dissolved, the olivine and the pyroxene dissolved, and then reprecipitated as phyllosilicate, then you'd end up with this kind of brick brown colored phyllosilicate mass that you see in the more common type 1 material. Okay, and now we're going to look at the oxygen isotopes of Bennu and Ryugu. So these also show CI-like compositions, and Richard is on this call, knows a lot more about this than I do. But they span a range, and they span from CI compositions to CY compositions, and even beyond for Bennu, even to more O16 pore values. Okay, can't remember if there's anything else that I want to say about that. Oh, yes, I do want to say something about that. So what I wanted to say is, although we have like this incredible range of what I call the CI family material, they range massively in delta 18O, but this range is not necessarily related to increasing alteration. So Mike Zelensky and Sarina Goodrich also made this point, that increasing alteration doesn't drive it to more O16 pore values, as you might expect. And why is that? So Sarina and Mike suggested this means that they must have accreted different material to start with. And we can actually test that by looking at Bennu, I think. So we have some oxygen isotope values for some pyroxenes and olivines from Bennu, which I'll show you. So some of this work has already been published by Barnes and Nugent et al., and we have some in review as well. So what we see is that the olivine and pyroxene, we have one spinel analysis too. The olivine and pyroxene values fall into two camps. One very AOA-like, so very O16 rich. And about half of the particles we analyze fall in this camp. Then the others show quite a large span of range from chondrule-like material to values that are really heavier than we often see in chondrules, to values that are above the terrestrial fractionation line, which is very unusual for carbonaceous chondrite material, and heading up towards bulk Bennu. So I think this shows that it could be pretty easy to have small differences in these accretion, the stuff that you accrete, which would produce a bulk difference in the oxygen isotopes. Because there's such a huge span in oxygen isotopes of the original material accreted. Okay, so now I'm going to slightly change track and talk a little bit about what happened after accretion, the post-accretion reprocessing. And this is work that, again, is already published, the references at the bottom. So what we can see petrologic evidence for is that the phyllosilicate precipitated fairly early on. And then the bugs in the phyllosilicate would have filled with water and produced these later salty minerals. So that includes the calcium carbonate, which would have precipitated first, making these nice crystal shapes. Then you can see the magnetite crystallized around it, precipitated around it. And then finally, there's an unusual magnesium sodium-rich phosphate in Bennu, which just infilled the remaining space. So that formed later. In some samples of Bennu, we see other salts as well, including sodium chloride and potassium chloride in this image. And putting this all together, we think that all of these salts actually form a sequence which we have pieced together. And by comparing as well to evaporites on Earth, we can see how this reflects the evolving fluid composition. So the fluid would have started out fairly neutral. Then after the carbonates precipitated, it was driven to more alkaline compositions. And what we see at this point is that probably the fluid then would have been incredibly briny and would have formed little pods of water, room temperature water in Bennu, from which these last salts formed by evaporation. So this has got several implications, but for the point of this talk, I just want to point out this means that the water-rock ratios would have been really high in Bennu. So there would have been an excess amount of water even after the phyllosilicates had all formed. We can say something about the temperature of alteration. So this is work done by Catherine Harrison. There's a picture of her there with the llama. And also it's reported in Zager and McCoy. So she and colleagues looked at a composition of sulfides in detail and compared it to known compositions at various temperatures, and they found that the best match for the known phase diagrams for sulfides is at around 25 degrees, so around room temperature. We think this is the kind of temperature at which this alteration happened. Okay, so then we can start to piece together something about the water-rock ratios and the temperatures at which the alteration happened. And again, I'm looking at two main camps, the CI-like and Bennu, and probably all of that kind of family of material formed at high water-rock ratios and low temperatures. Whereas the CM1s, and we also have good data for Flensburg, they formed at much higher temperatures because the toshilinite had disappeared, and probably at lower water-rock ratios, which were recently quantified by Moroshi et al. So just to kind of like give you a visual impression of how I see these differences, the CIs would have formed something like in a cold bath, so loads and loads of water, but very low temperatures, whereas the CMs, more like a steam room, hot temperatures, but not so much water available. But in both of them, they produced these alteration reactions, both of these environments. Okay, so I'm kind of broadly dividing these objects into two groups, the CI-like clan and the CM-like clan. And again, these are very, very kind of big families. but the CIs include Bennu and Ryugu as well, and the CMs include Flensburg. So they have a matrix that includes saponite as well as serpentine. They tend to fall above the terrestrial fractionation line in oxygen isotopes. They have no chondrules, whereas the CMs have evidence for having contained chondrules once. And then, as we discussed, the CIs formed at high water rock and ratios and low temperatures, and the CMs at low water rock and high temperatures. The fluid compositions were different as well. So the CIs, especially, they evolved to alkaline compositions, whereas the CMs were less alkaline. And that's work by Schreider et al. Okay, so I'm getting towards the end, although I hope you don't mind staying a bit longer. So I just want to talk about how many parent bodies. So when the whole kind of classification system for chondrites was developed, we didn't know that there were so many asteroids out there, basically. In 1980, only 43 near-Earth asteroids more than a kilometre across were known. So it sort of made sense that maybe one meteorite group means one asteroid. But now we know there are many, many more asteroids. But Richard Greenwood's work showed that only 95 to 148 meteorite parent bodies are required to explain all of our meteorite collection. So then the question is are meteorites unrepresentative of what's out there? That's almost certainly true. But also they have other ideas as well. So it could be that there are a smaller number of parent asteroids which then broke up into smaller asteroids. But then also I think this is an interesting idea that Greenwood et al. Suggested. There are asteroid clones. That is, there are asteroids that are similar to each other and produce similar meteorites. Meteorites of the same group, but actually there are multiple parent bodies. And so this is the idea that I'm going for. So I think that the multiple parent bodies can explain this great diversity of CEI-like lithologies, especially the huge variations that we see in xenoliths and micrometeorites. And so there may be clone asteroids in the outer solar system. And I'd argue this is actually what you'd expect, because they have a solar system like bulk composition. So you basically expect all asteroids to be like this, to be CI-like, especially in the outer solar system. So I don't know if I've written this in the right order, but yeah, it's because we see this huge span of textures and minerals and oxygen isotopes. So that also argues for multiple parent body. And also the fact that most of them are regolith breccias, which I think implies that they mostly come from small bodies, mainly maybe tens of kilometers at the most. And that also because we don't see many metamorphosed examples, but there must be at least one larger body, because we see minerals like tremolite, which only forms at higher pressures. And that's discussed in Hamilton et al. Okay, so this is the way I see it. The non-carbonaceous chondrites formed in the inner solar system between the Sun and Jupiter. And beyond Jupiter, the carbonaceous chondrites were formed. The CMs probably formed in a pressure bump maybe around Jupiter. And here they would have formed of bodies maybe a little bit bigger than the CIs, where they were hot enough to reach type 1 temperatures in the center. Whereas the CIs formed in the outer solar system beyond Saturn. And there's other evidence for this as well. There's the high ammonia abundance in Bennu, for example, which suggests that it comes from the real outermost part of the solar system. So my prediction would be that the petrologic type varies according to radial distance from the Sun, from 3 close to Jupiter to 2s where the CMs were formed, and then the 1s beyond Saturn. And then I think if you go even further out, you start to accrete with more ice, and that means that you'll have less aluminium-26. So you might start to reach a situation where you don't get so much aqueous alteration anymore. They're similar to what we see in the WILD-2 silicates. B-type asteroids may be more like that, maybe a mixture of just anhydrous silicates. Okay, so I hope you would agree with me that type 1 material is abundant in space. So why don't we see it in our meteorites? So there are several reasons. Delivery to the near-Earth environment, maybe there aren't that many near the Earth. Survival through the atmosphere, survival on the ground. And then when they're on the ground, they're not really recognized as meteorites. So of these options, I think they all, no, they don't play a role. The first one doesn't play a role. And we know that because Bennu and Ryugu, which are near-Earth asteroids, are both type 1. But the other three do play a role. And I'll just finish with two little stories about this. So firstly, they don't survive very well on Earth. And I love this quote from Follansbee, who has described the Revelstoke meteorite fall. He says, it's a material as perishable as the alchemist's earth, air, fire, and water, and not very stable in any of these media, which I think is very poetic. And then the story, which is described by Zunel and Zelensky in 2014, is that when Orgay first fell, one of the stones was given to a Professor Peredew, and he put it in water because he wanted to measure the density, and it just immediately turned into mud. So he lost his sample and his analysis. And that just goes to show how easily it's destroyed in the Earth's system. If a CI meteorite falls and it rains, then it may just be lost forever. And the final story is about one of my predecessors. So this is George Thurland Plariah, who worked at the Natural History Museum 100 years ago. He was a chemist who did a lot of the initial classification work on meteorites. Oops, I want to go back. And this is his lab notes about Allais. And I don't know if you can read his writing, but what he wrote is, thought this specimen was a bit of the soil picked up in mistake, and thus nearly threw it away. Looked up information and found it to be bona fide, therefore of special interest. And then he goes on to wonder if this is actually soil from another planet. And if that's the case, does that mean that planet has got life on it? Which I think is a really interesting thing for him to wonder about. So I will leave it there. So broad conclusions are there's a huge variety of type 1 material, much beyond what is seen in CI chondrites, which are often just called all type 1s, and beyond what is seen in major meteorite groups. Bennu and Ryugu, we now know, are near-Earth asteroids, which are composed of type 1 material. And this suggests that our meteorite collection is incredibly biased compared to what's likely represented in asteroids because of the fragility of this material. So I think CM1s probably formed in the interior of CM parent bodies. And I think there are multiple CI-like parent bodies which explain the huge range of compositions that we see in these materials. So I will leave it there. Richard, shall I stop sharing?
Yeah, that would be great, Sara, if you wouldn't mind. Yeah. I think what I was going to say was that in the past we've done the chat by the question and answer by people putting the stuff in the chat, and I was just wondering whether if we try as an experiment, what I'll do is I'll allow people to unmute themselves, and then they can actually ask a question. So I'm just going to do that now.
Great.
So you should be able to unmute yourself. So if anybody would like to ask a question, then they can do so directly. We'll see if that works.
Well, hi there. This is Alan Rubin. Can you hear me?
Yeah, we hear you loud and clear.
Hi there, Sarah. Very nice lecture. I wanted to thank you, but I also add a question for you. And that is, when we were separating olivines and orgay, we found that the isolated olivines sometimes associated with pyroxene and one or two times have tiny little bits of metal in it. They looked like chondral phenocrysts. And when we measured the CaO versus olivine phayolite, their distributions were nearly identical to those in CM chondral phenocrysts, suggesting to us that there's this commonality between the anhydrous minerals in the CIs and in the CMs. So I was wondering your proposed dichotomy between them, how this would fit into that.
Yes. Okay. Great question. Thank you, Alan. So I think, so did you mechanically separate the silicates? Yes. Okay. So I think that firstly, we also see, well, I've seen one or two metal grains inside olivine, and we actually got an oxygen isotope measurement of that, which showed it was chondral-like, and we agreed that ours also looked like CM2 chondral material for that olivine fragment that had metal in it. So I think there is some commonality. So there are definitely some chondrite-like material in Bennu, and the chondrite-like material, you're right, is similar to that in CMs. Absolutely, yes. So maybe, maybe that means this material, this chondrite-like material, was kind of floating around before the giant planets and could mix freely between across where eventually Saturn formed, perhaps. So maybe that's it. The other point, of course, is that if you mechanically separate it, you get the larger grains, and we found that those are more likely to be chondrite-like, whereas it's the smaller ones that tend to be more kind of AOA-like. So we don't, so we'd see more AOA ones if you do kind of in situ measurements.
Okay, thank you.
Thank you.
If somebody else would like to ask a question, please go ahead.
Hey, Sarah, it's Martin Buttle. Oh, sorry, speaking at the same time as someone else. I'll let whoever else was speaking go first.
Okay, sorry. This was actually Guy Consolmagno. I'm
hi,
Zoom
Guy.
user here because I can't figure out how to change my name. Do we have reaction rates information for some of these reactions happening to the water to material to make phyllosilicates? In other words, can you estimate for the things that were in the water bath, how long would they have to have been immersed in the water to see the reactions?
Well, I mean, all I'd say about that is that we have some age dates for carbonates, they're of the order of kind of 10 million years or so, I think, off the top of my head. So that's the kind of order of magnitude that we're thinking. But Martin, who was just about to ask a question, has done some experimental work as well, looking at this alteration. So I don't know if you want to comment on it, Martin.
Oh, yeah, thanks, Sarah. Yeah, I mean, well, the experiments we've done have been taking CO chondrites and trying to make them into CMs, or at least exploring that aqueous alteration. And my PhD student Bianca is on the call, has taken that work up. If I was to say steal one of her findings from her recent work, we found that actually altering them on the scale of, say, 100 days, they alter not that much. They get to an effective water-rock ratio of about 0.2. So it looks like you need orders of magnitude longer, I would have thought, to produce these types of materials, which is consistent with what you're talking about. But then I'm surprised that any pyroxene at all survives.
In what? In Bennu, or what do you mean?
In Bennu and in any other CI material. You showed a few pyroxene.
Yeah. So I mean, olivine is much more abundant than pyroxene in most class of Bennu, not all, but most. And maybe at a kind of 8 olivines to every 1 pyroxene, something like that. So, and the pyroxenes tend to look more corroded than the olivines. So they're definitely not surviving quite so easily, but yeah, they're there.
Sure, it's very odd. The question I wanted to ask was about the CY1s, if I may.
Well, you can, but I'd just like to point out you are an author on this talk, Martin. So no difficult questions.
Well, I can't promise that. So since writing my CY paper where I suggest there's CY1s and CY2s, you noted a bunch of, I think there were 2 main papers, Zhu et al. And Schrader et al. That kind of, say the CY1s are heated CIs.
Yeah.
So how do you get such high sulfide abundances? If they're heated, you would think that they've got to have had sulfide decomposition within the body, migration of sulfur, and then enrichment in the layer that becomes the CY1s. And if that is the correct model, and really that's the only way I can think that would make sense, then we should see corresponding CY1s which are depleted in sulfur, and we don't.
Yeah. I don't get that either. I don't really understand the sulfide thing. I think maybe someone needs to do some experimental work to see.
It's really interesting. There's something weird about the CYs, why they have so much sulfur.
For sure. Yeah, I agree. They've got so much sulfide in them. It's incredible.
Thanks for a lovely talk, Sarah.
No, thank you.
If anyone else would like to ask a question, please go ahead and do so now. The chat is also open, actually. It was temporarily closed, but you can ask a question in the chat as well if you'd like.
Hi there, Sarah. This is Alan Treeman. You
Hi.
mentioned Antarctic carbonaceous chondrite that had amphibole, and I missed what its name was. Could you repeat that, please?
Well, the amphibole was tremolite, but the meteorite, there's one meteorite which is Miller range. Can't remember its name now, but the one that used to be a CR1, but now it is anomalous. Let me check the name.
Of
Or
course,
unless anyone else, I'm sure probably someone on the call knows, but it's Miller range 0900292, and it's also, but it's also found in classed in Alma-Ata-Sitta.
Right. Yeah. I mean, I've been working with Serena Goodrich and a couple others about the
Okay.
abilities.
Yes. Right.
It's very interesting that these large evidence for large objects early in the solar system that apparently are no longer there. So.
Right. So you would agree with that? That
Yeah.
you must have something the size of Ceres?
Absolutely. Yeah.
Well,
I'm a co-author on that Hamilton paper. So.
Right. Okay.
Yeah. So of course I agree with it.
Right. And it can't be due to kind of a shock or something like that. It has to be a longer term pressures and temperatures.
Yeah, that's the impression. Yeah. I think it takes a while to do that. The harder one for high pressure is that eclogite classed in the CR chondrite. I forget its name, but that one's again evidence for very high pressure somewhere inside a early solar system body. But thanks.
Thank you.
Do we have any more questions for Sara? That sounds well. In the absence of any more questions, Sara, it's a very big thank you for a very, very interesting talk. Thank you very much.
Thank you very much. Thank you, and happy holidays, everyone.
Yep. I'll stop recording there now. So it's just okay.